Welcome to Lecture 3.7, Cauchy-Euler equations. This is going to be the first time that we see second-order differential equations where the coefficients are not constants, but rather have variables in them. Solving these equations is going to be the focus of the remaining lectures in this section, although this lecture is going to focus on probably the simplest class of these equations, namely the ones called Cauchy-Euler, and that their solutions are going to be very simple indeed. So in this lecture and the remaining ones in this section, the variable is going to be x for position rather than t for time. A lot of these equations arise naturally in physics and engineering. I guess the ones we saw earlier did as well, but those are naturally functions of time. Think like simple harmonic motion, where these equations, when they come up, are typically going to be functions of position. Things like the velocity or the displacement or the temperature as a function of position. Okay, so let's get started. Here's a second order homogeneous differential equation, and y is a function of x, and the coefficients now involve the variable x. So here's what we know right away. We know that the general solution is going to be like c1 y1 of t plus c2 y2 of t. So all we have to do is we got to figure out a y1 and y2 that work. This is generally going to be the game with these type of equations. So what's a good guess? Well, when these were constants, so if this x squared and x, if these things were just 1, then remember we would guess that y of t would be e to the rt. And the rationale for that is when we took derivatives of this and we plugged them back in, if these variables were not there, then every term is going to have the same form, some number of e to the rt's, and for the right choice of r, we could make that work. So that's not going to work here. And well, if you want to see why, let's try it. Let's try that. So y prime of t equals r e to the rt, and y double prime of t, I should be saying x, equals e r squared e to the rt. Okay, so let's just suppose that these things were x instead of t, and let's plug this back in. Let's see what's going to happen. So we're going to get x squared. Now y double prime is going to be r squared e to the rx. I need to switch back to x, plus x r e to the rx minus e to the rx equals 0. And you see why this is not going to work? Because we have an x squared here, an x here, and a negative 1 here. So in other words, if we simplify this, we get x squared r squared minus xr minus 1 times e to the rx equals 0. That's not 0, so this thing here better be 0. And that's not possible. There's no value of the constant r, which is going to make this the 0 polynomial. Maybe what if r is 0? Well, that's not going to work either because there's negative 1 here. So this whole thing does not work. So what do we do next? Here's one thing I want you to notice. Notice that for each derivative here, there's an extra power of x. So let me propose this. So let's guess a solution. Y of x equals x to the r. Now why is this a good guess? Okay, so let's take some derivatives. If we do that, y prime of x equals r x to the r minus 1, and y double prime of x equals r minus 1 times x to the r minus 2. So now here's what I want you to notice. When we plug these things into here, so each time we have a plug in a derivative, we're losing a power, I guess a factor of x, but we're gaining that right back because there's an x here and an x squared here. In other words, when you plug back in, let's try it and see what happens. Plug back in. So x squared y double prime is x squared, y double prime is r minus 1, x r minus 2. plus xy prime, that's plus x times y prime is r x r minus 1. And then minus y is minus x to the r minus, sorry, just x to the r equals 0. And look what happens. Every term here is x to the r. So let's simplify this, and we get r times r minus 1 times x to the r plus r times x to the r minus x to the r equals 0. So let's factor out an x to the r. X to the r times, okay, now what do we have here? We have r squared. We have minus r plus r, so those cancel, minus 1. So r squared minus 1 equals 0. In other words, r equals plus or minus 1. That means we have a solution of the form x to the r. So differently, y1 of x equals x to the first, and y2 of x equals x to the negative first. So now we have our general solution. Y of x equals c1x plus c2 x to the minus 1. Take a moment to think about why that worked, and it all came down to the fact that for every derivative of y here, think about if you have a solution x to the r, when you take a derivative you lose a power of x, but you gain it right back because y prime is coupled with this x, and y double prime is coupled with this x squared. Okay, so you probably know what's coming next. Here's a differential equation, and we do the same process. We're going to get roots that are complex instead of real. Okay, so here's a homogeneous equation. We notice that for each derivative of y, there's a suitable power of x in front of it. So this is what we call a Cauchy-Euler equation. So we are going to assume that the equation has the form x to the r. We plug this back in. Oh, let me take derivatives first. Y prime of x equals r x to the r minus 1. Y double prime of x equals r times r minus 1 x to the r minus 1 minus x r minus 2. Okay, so we plug this back in, and we get x squared times y double prime, which is r minus 1 x to the r minus 2, plus x times y prime, which is r times x to the r minus 1, plus y, which is x to the r equals 0. So let's simplify this. Make sure you understand where this is coming from. This is y double prime, this is y prime, and this is y, and we're just plugging these guys into this equation. So simplifying, we get x to the r. Notice every term has an x to the r in it, so we're gonna factor that out in front. And now let's simplify what we have. We're gonna have an r squared. Ooh, my pen back. Let's have an r squared. I don't know if I'm going to be able to do this in my head. Oh yeah, I can. So this is going to be r squared. Well, let's write it down. Minus r, then plus r from here, plus r, and then plus 1 from up here. Plus 1 equals 0. So this is going to simplify as x to the r times r squared plus 1 equals 0. So this means that r is going to be plus or minus I. So that means that we have two solutions. We have y1 of x equals x to the I, and y2 of x equals x to the minus I. So unpredictably, or I should say predictably, unsurprisingly is what I meant to say, we're not satisfied with solutions of this form. We want to actually write these in things that we can understand. We want to write these in terms of real value functions. So let's do that. So how do we do that? Okay, so here's something I want you to notice. I'm going to take x to the I, and I'm going to simplify this, or not simplify, but I'm going to rewrite it. This is a trick that occurs a couple times throughout differential equations. x, I'm going to write this a fancy way. I'm going to write this as e to the natural log of x. Do you agree with me that that is indeed x to the I? Okay, why did I do that? Well, that's just e to the I natural log of x, and I bet you know it's coming from here. Yep, Euler's formula. Remember that? E to the I theta equals cosine of theta plus I sine of theta. So this reduces down to cosine. My theta now is natural log of x. So cosine of the natural log of x plus I sine of the natural log of x. And similarly, e to the negative I is e to the natural log of x. That's my x. To the negative I, which is e to the negative I natural log of x. So this is cosine of the negative natural log of x. So negative natural log of x plus I sine. I'm going to hold off on writing the plus sign of the negative natural log of x. Do you remember that when cosine of negative x equals cosine of x, so this negative sign gets absorbed, and I'm going to make that plus, and this negative sign pulls out of the sign, because, again, cosine of negative x equals cosine of x, and sine of negative x equals negative sine of x. So we can pull out this negative sign and make that positive. And so what do we have? We have y1, this is y1, and this is y2. And we're looking for real valued solutions. So let's do what we did before. Let's add these things up, and the signs will cancel. So in other words, y1 plus y2, 1/2 y1 plus y2, is cosine of the natural log of x. And similarly, if we subtract these two, so let's subtract them, y1 minus y2, is that a legible y? Let's fix it a little bit. y1, I think I'm going to have to fix the whole thing. y1 minus y2, what's that going to be? That's going to be that's going to be 2I sine of natural log of x. So let's divide by 2I to get rid of that. So this is sine of the natural log of x. So these things form a basis for the solution space. I could write c1 x to the I plus c2 negative x to the I. And let me say that. So because of this, I could write y of x equals c1 x to the I plus c2 x to the negative I, but because of these, I instead prefer to write y of x equals c1 cosine of natural log of x plus c2 sine of the natural log of x. And this is my preferred solution right here. Again, these things, this and this, they generate the same family of solutions if you allow C1 and C2 to be complex numbers, but just this is a much nicer thing to look at and work with. Okay, so predictably, you knew this was coming. Here is an example where we have a homogeneous differential equation. This is a Cauchy-Euler equation, and the polynomial that we're going to get in R is going to have a repeated root. Okay, so by now you know the drill. So let's do this, and I'm going to move a little bit quickly in the first few steps because you've seen this before. So we're going to assume that the solution is of the form x to the r. So y prime is r x to the r minus 1, and y double prime equals r times r minus 1 times x to the r minus 2. Okay, so when we plug this thing back in, we have x squared times r minus 1 times x to the r minus 2. This is my y double prime. we have 3x times y prime, which is r times x to the r minus 1. And then we have plus y, which is x to the r. And if we simplify this, well, we have an x to the r in every term, and we can factor out, this is how many r's do we have? We have r squared minus r plus 3r plus 1, so that's going to be r squared minus r plus 3r plus 1. So this is x to the r times r squared plus 2r plus 1 equals 0. So this is the r squared, of course, we divide that out because that's never identically 0. And so we get r squared plus 1 squared equals, not r squared minus 1, r plus 1, quantity squared equals 0, so r equals negative 1. That means we have a solution of the form y1 of x equals x to the minus 1. So next, well, I say next because this only gave us one solution. We need to somehow come up with a second one. So how do we do this? That's going to be the same method that we usually use, and it seems to always work when we have a repeated root, is that we guess that there is a solution that's slightly more complicated. This is like a variation of parameters type thing. So we're going to look for a second solution to be some function v of x times our original solution, x to the minus 1. And we're going to solve for v of x. Okay, so let's do this. Well, first of all, instead of writing y2 everywhere, I'm just going to write y. So I'm going to write y is x inverse v. Let's take derivatives. Y prime is going to be x inverse v prime minus x to the minus 2v. That's just the product rule. And y double prime is going to be, let's be careful here. Let's take the derivative of these two terms separately. So the first one, the derivative of that is going to be x to the minus 1 times v double prime. Then that's going to be minus x to the minus 2 times v prime. So that's the second term for this first term, right? And the second term, derivative of that, let's put that in parentheses as well so we can keep track of it. It's going to be x to the minus 2 times v prime minus 2x to the minus 3 times v. Okay, so let's simplify that a little bit. That's going to be x to the minus 1 times v double prime minus 2, that should be an x, to the minus 2 times v prime plus 2x to the minus 3 times v. And yeah, so next thing, let's plug this back in. Plug back in. So we're going to plug into this equation, boxes so we don't lose it. So, okay, so x squared y double prime, that is, that's x squared times this creature, x minus 1 times v double prime minus 2x to the minus 2 times v prime plus 2x to the minus 3 times v. Okay, so next we have 3xy prime, that's 3x times this thing. So 3x times x to the minus first times v prime minus x to the minus 2 times v. And then finally plus y, that's just this term. So that's plus x to the minus 1 times v, whole thing equals 0. Okay, so let's simplify this. So how many v primes do we have? So we have x times v double prime. That's the easy term. Okay, so how many v primes do we have? Let's write this out. v primes, let's count them. So we have negative 2 times x squared times x minus 2, so that's going to be just negative 2. And then how many others do we have? We have, where's another v prime? V prime is here. 3 times x inverse, so that's plus 3. Times v prime, and that's it. And then how many v's do we have? So v's, let's count them. There's a v. That's, the coefficient is 2. 2 times x to the minus 3 times x squared, that's going to be x to the minus 1. We have another v up here, that's going to be minus 3. So minus 3 x inverse times v. And then we have a 1 here, so plus x inverse times v equals 0. Unfortunately, this whole thing cancels, and it's sort of a general theme that when we guess our solution the way we should and we plug it back in, if we've not made a mistake, things should massively cancel. So now what we get is we have a, so also this thing simplifies just to positive 1, so that means that we have, this differential equation massively simplifies. It's x v double prime plus v equals 0. So once we solve this, then we will have our v and we have our second solution. Okay, oh, I'm sorry, it's a v prime. So this is a second order equation. You may say, how the heck do we solve this? But it's really just a first order equation, right? I mean, because, you know, this is v prime and v double prime. If we call v prime a new function w, then we just have w and w prime. So let's do that. Let's let w equal v prime. So w prime equals v double prime. So really this equation, I'm thinking of it as x times w prime plus w equals 0. That's a better way to write it. So let's solve for w, and then so once we have w, then we just integrate that to get v. So how to solve for w? Or we can separate variables. Yeah, let's separate variables. I was going to say we could do the integrating factor, but separating variables, when we can, it works. Okay, so let's write this as x times dw dx equals negative w. Okay. So by separating variables, that means we put the w's on one side. So we have dw over w equals, let's be careful here. So dw over w equals dx over s. Somewhere I'm going to have to put a negative sign here, so it doesn't really matter where I do it. Let's do it there. So now let's integrate both sides, and I'm going to put the integral inside the negative sign. So now we get, I'll continue over here, so we get the natural log of w equals negative the natural log of x plus c. Okay. Did I do things correctly? I think so. So from here, we have, so let's exponentiate both sides. So the left side is w, and the right-hand side is, we can always move the c down, c times e to the, let's get really careful with these negative signs in here. So this thing, so this is e to the natural log of x to the negative 1. Agreed? And that's c e to the, not e anymore, c times x to the minus 1. Okay, so this is the general solution. We don't need the general solution. You know, all we need is any solution. We don't need a general solution for v. We just need any v. And so to find any instance of v, we need to find any instance of w. So this is the general solution for w. So here's the w that works. W of x equals 1 over x. This is one solution. And that's all we need is one solution. So if w of x is x to the minus 1, or 1 over x, then that means that v of x, this guy, that's the integral of w. That's the integral of w of x. That's going to be the natural log of x. And again, I do not need a c in there, a constant. You know, technically, v would be c1 natural log of x plus c2, because we should keep this c and keep that c. But again, we only need one solution. And here's our solution. So that means v equals natural log, make this clear, v equals the natural log of x, which means y2 of x, remember that up here? y2 of x is the natural log of x times x to the minus 1. And so our general solution is y of x, so it's c1 y1 of x plus c2 y2 of x, which is c1 x to the minus 1 plus c2 x to the minus 1 times natural log of x. And there is our solution. And now I will say that it turns out that this is always going to work for anytime you have a repeated root, and you guess a solution like this, you will always get the natural log of x for v. So in general, you're going to get c1 e to the r plus c2 e to the r times natural log of x. Okay, so I'm going to show you an alternate way to solve Cauchy-Euler equations. And I wouldn't recommend it for the first two examples, but for that third example, with that repeated root, which is what we have here, it's going to actually make it a lot easier. And what it's going to be is we're going to do a simple variable substitution, and it's going to, and we change variables. This variable coefficient equation is going to turn into a standard constant coefficient equation, which we know how to deal with. So here's the substitution that we're going to do. We're going to let t be equal to the natural log of x. Okay, so now y of x, so instead of thinking of this thing as a function of x, I want to think of it as a function, I want to think of this as a function of t. So y of x is some other function of t, or some other function of natural log of x, which is u of t. So I want to write this thing as a differential equation in u of t. So to do that, I need to write the derivative, so dy dx by the chain rule. So the derivative of y with respect to x, so the derivative of this thing with respect to x is u prime times the derivative of the inside. So that's u prime times 1 over x. So that's going to be du dt times 1 over x. And then the second derivative, d squared y dx squared. So that's the derivative of this thing with respect to x. So that's going to be, so what is that going to be? So by the product rule, that's going to be the derivative of this with respect to x. Let's do that one first. D, again, that's going to be d squared u dt squared times the derivative of natural log of x, dx dt. So that's 1 over x. Let me just emphasize that this is dx dt plus du dt times the derivative of this. So plus du dt times the derivative of x, which is not the derivative of x, the derivative of this, which is minus 1 over x squared. So this here is the derivative dx of 1 over x. So this thing is, what does this simplify to? 1 over x squared times u double prime minus u prime. And by prime, I mean this is going to be in terms of with respect to t. So now we're going to plug this thing back into here. Let's see what happens. So we have x squared times y double prime, which is 1 over x squared. Oh, I did my squared first. 1 over x squared times u double prime minus u prime plus 3x times y prime, and my y prime is this, so that's u prime times 1 over x plus y, and my y is just, y of x is u of t, so that's u equals 0. And let's simplify this. So notice that things cancel, those cancel, these cancel, and so what does this become? So this becomes u double prime, and then we have plus how many u primes? 3 u primes minus 1 u prime, so that's plus 2 u prime, and then we have plus u equals 0. Now we know how to solve this. We're really good at this, right? So the characteristic equation, we can write it out. This is r squared plus 2r plus 1, which is r plus 1 quantity squared equals 0. So we know the general solution. Even though this is a repeated root, we know that u of t equals c1 e to the negative t plus c2 times t e to the negative t. Remember with a repeated root, we just stick a t in there? And the same method works even in the non-repeated root case. It's just that in the repeated root case, it actually provides a shortcut for what we did in the last slide. That was a disaster, but it did work out. So here's u of t. Okay, so u of t, so what are we trying to solve? We're trying to find y of x. Y of x is u of the natural log of x. So let's plug the natural log of x in for these values of t. So this is c1 e to the negative natural log of x plus c2 times, what was t again? T is the natural log of x. So c2 times the natural log of x times e to the negative natural log of x. So let's simplify this. This is c1. It's so easy to make mistakes here with laws of exponents. So let's write this as e to the natural log of x to the negative 1. Agreed? Plus c2 natural log of x times e to the natural log of x to the negative 1. See what I did? Anytime you have an e to the something times x, write it as e to the something times natural log, write it as e to the natural log to the something. And now, this is y of x. Now I can simplify this. Y of x equals c1. Now this is just x, and this is x. So this is c1 times x to the minus 1 plus c2 times natural log of x times x to the minus 1. And now you can see why this is going to work. This is really going to be a shortcut. And again, this doesn't just, so this is the same thing we got in the previous slide, got it a lot quicker. And so these Cauchy-Euler equations, they're really just these constant coefficient equations in disguise if you do a clever little change of variables.